Morning, everyone. So welcome to the morning session. I'm Shuoqing, a Chen instructor at BIMSA. So I'll be your chair for this morning session. So today this morning we have three excellent talks ahead, each lasting 55 minutes, followed by 5 minutes for question and answer, with 10 minutes break between them. So to begin, our first speaker is Professor Fabio Cavalletti from the Università di Milano.
Yes, perfect.
Professor Cavalletti is renowned for his contribution to optimal transport theory and geometric measure theory. Today, he will present on optimal transport between algebraic hypersurfaces. So please join me in welcoming Professor Cavalletti.
Thank you. So thanks for the nice presentation and for the invitation to deliver this talk. So my main field of expertise is optimal transport, but in this presentation I will like to talk about a recent project where we try to merge techniques from let's say complex algebraic geometry and optimal transport. Okay, so. So the question that we try to understand was what is the optimal way to deform, let's say, a special class of submanifold that are the projective hypersurfaces from one projective hypersurface to another one. Okay, and so this is, let's say, the algebraic part. So since my point of view is from optimal transport, we try to address this question using the language and the techniques from optimal transport theory. So our idea was to associate to a projective hypersurface a measure, and then consider the problem of transporting one projective hypersurface to another one via this transport of measures. Okay, so the talk will be very basic. So I will basically introduce all the objects that we need. So maybe for some of you will be a bit basic, but yeah, since the topic is a bit between two different fields, it's better to recall all the necessary details. So the plan will be then to associate to a given hypersurface of a certain degree, a probability measure, then define among this class of measures that you have obtained a distance induced by the unoptimal transport problem, and then see if this new metric that you have introduced on the space of polynomials will actually have some consequences, okay, and application. So this project has been carried out in collaboration with two other guys from CISA of Trieste, when I was there also around 2020, that are Paolo Antonini and Antonio Leradio, okay? Okay, so let's start from really from the basics, from the beginning. So let's start introducing what for us is a projective hypersurface. So what we do, we fix the set of homogeneous polynomials plus one variable of a fixed degree of degree d. So this is very simple. So it means that you have an homogeneous polynomial of this form. So z will all this z variable will be in C, and also the coefficient. Okay, and for any homogeneous polynomial, what you know is that its zero set, it's naturally a subset of the projective space of dimension n, so of CPn. So the n plus one tuple of complex numbers that are identified up to a multiple of complex multiple. Okay, and so to any polynomial, you have this projective upper surface associated to it. And in CPN, you have a very natural metric that is the Fubini-Study-Hermitian structure. And it's the one that you induce simply by considering CPN as the quotient of the sphere of dimension 2n plus 1. Okay, so CPN is, you can see it as a quotient of CPN, of S2n plus 1, once that you consider the multiplication by an imaginary number, okay? So you want this projection to be a Riemannian submersion. So the Fubini-Study-Hermitian structure, you have to think about like the most natural metric that you can put on CPN. So to any homogeneous polynomial, we have this projective hypersurface that it's a subset of CPN with a very nice geometric structure. And what is the regularity of the zero set of an homogeneous polynomial? It could be singular, depending on the polynomial that you have considered, but it's always, I mean, CPN, it's a compact manifold, so ZP being the zero set will be complex, so it's just not any submanifold, but it's a complex submanifold, and it will have real dimension to n-2, okay? The possibility of being singular, it's actually, you have a special subset of polynomial that is called the discriminant, so that will be denoted by this delta ND, that this is a subset of the space of homogeneous polynomials, and is the set of polynomials for which Z of P it's a singular, it's singular. For us, singular means that the equation that is defining the submanifold is singular, means that there exists not just there exists a point in Cn plus 1 that annihilates both the polynomial and its derivative. Okay, so it's the equation that it's singular. So a priori, ZP could be a smooth submanifold, but the equation defining it could be singular. Okay, so so far so good. So these are the space of homogeneous polynomials. If you are outside of the discriminant, so I recall you P and D homogeneous polynomial in n plus 1 variable and degree D. Delta is the discriminant where the things go bad in terms of the equation defined at zero set. If you are outside of the discriminant, its zero set will be an oriented smooth complex submanifold of CPN, and therefore recall that the first step that we want to do is to associate a probability measure to any homogeneous polynomials. So in this case, it's rather simple. You can just directly restrict the volume measure induced by the Fubini structure, the Fubini study structure of CPN. So you have a smooth submanifold of CPN. On CPN, you have a Riemannian metric, Hermitian, super nice. You just restrict the metric and you consider the volume measure. Okay, it's just like this. The important part, however, is since you want to deal with the optimal transport, it's a distance that usually you have between probability measures, because you want to transport measures having the same volume. You do not want to have different volumes, otherwise the situation is, it's slightly more complicated. But so the important fact is that if Z of P is smooth, so if you are considering a polynomial that's outside of the discriminant, then the volume, defined like this, does not depend on the polynomial. It's just a fixed constant. So its volume, it's just the degree times the volume of CPN minus 1. Okay, so it's like the same thing that you would have on a simple polynomial, so the fundamental theorem of algebra. If you have a polynomial of one variable of degree D, it will have D complex root. Okay, so this is the same. So this is, let's say, the higher dimensional observation that you would have when you consider polynomials of more than one complex variable. So the volume of this family of submanifold does not depend on the polynomial. So it's just a constant that depends just on the degree and on the dimension that you are considering. You can see, for instance, this fact by considering what is called the kinematic formula. That means you just, to measure the volume, you can just, let's say, take Z of P and just count the intersection with complex lines. But it's not necessary to just focus on this formula. Okay, so as I was mentioning, yes, in dimension 1, you know that this fact just means that the number of complex zeros just depends on the degree and not on the particular polynomial. It's always equal to D. So what it means that you can recall that our plan for the moment is to associate to any homogeneous polynomial a probability measure. And so if you are outside of the discriminant, there is no problem. The zero set will be a smooth complex submanifold of a fixed volume that it will not depend on the polynomial. So therefore, our probability measure will be just the volume measure of the Z of P seen as a submanifold of CPN, renormalized by this constant that will not depend on the polynomial itself. And this map then will be a map from the space of homogeneous polynomial into this notation here, means the space of probability measures over CPN, okay? And this just means that if you want, you can see in duality with continuous functions over Cpn, and this means that this measure acts as the integral over z of t. Okay, so if you have a continuous unbounded function, a continuous function over Cpn, then this measure just integrate over the zero logos, as you would normally do. So this is very natural. Then what you want to do, you want to extend this map to, let's say, so the plan, this is not satisfactory. You need to extend this map to the whole PND, just not outside of the discriminant. Okay, so anyway, so far, so what we have done so far, so we have to think about like this PND, like any, let's say, linear space, because this will be, if you just, let's say, identify any polynomial with its coefficient, defining it, so this will be just a C to a certain power, that will, it just depends on the number of variables and degrees, so it's just a linear space. So at each point that it will be, we are identifying with this coefficient, along each point we will have, let's say, a smooth submanifold of Cpn, and then from here we are going to the space of probability over Cpn. Okay, it is just what it is. Okay, so the first thing that we have devised is that this is not totally surprising, but anyway, you need to work a little bit. That this map here, so this is what now I will call it in a different with an explicit name. So this map mu can be extended to a continuous map from not just PND. Let's say here we have P and D minus the discriminant, but actually, being a little bit more careful, you can extend this map into the whole PND, even on the discriminant, where you maybe have singularities, and you can do it so that the map, so going from PND to the probability measure, it's an homeomorphism onto its image here. Okay, and over the space of probability measure over Cpn, you have to, I mean, here over PND, you think just about the topology given by the coefficient, seeing as a subset of C to a certain power. Here you have the Weak-Star convergence. Okay, and again, here you have to be slightly careful because, I mean, if you go back and thinking about the one-dimensional, so the case of polynomial of just one variable, it could happen that you have, so the polynomial belonging to the discriminant are those having multiple zeros, and the way in which you want to extend a map associating to each polynomial, let's say its Dirac masses at the zeros, is that you have to take into account the multiplicity of the zeros. Here, obviously, it's slightly more complicated because here the polynomial will depend on many variables, so you cannot really just say that straightforward that you have a multiplicity of the zero. But anyway, let's say that going back and thinking about the formula that I've shown you before, the kinematic formula where you reconstruct the volume of Z of P just by counting the intersection with complex lines, more or less you can do the same. You count the intersection with complex lines and you count the multiplicity. So let's say that using an adequate generalization of the concept of multiplicity of zeros, that it's perfectly makes sense, it's perfectly reasonable, and for people that knows algebraic geometry much better than me, will be everything clear. But anyway, let's say that thinking about the multiplicity of zeros that you can define also in this setting, you are able, let's say, just by counting all of this intersection with CP1 and summing all over the possible CP1 as a subset of CPN, you will get an extension to a continuous map. Okay, so the first thing to fix in mind is that you have a well-defined map associated to each homogeneous polynomial of probability measures. This has to do with the fact that you start to count also multiplicities. Okay, so this is what we have called this map here, associated to a polynomial, the probability measure concentrated on its zero set. From our point of view, it's kind of the solution map, because what it does that to a polynomial, you associate a measure on its zero set. So it's kind of giving you a measure on the space of solutions to your zeros. As I was mentioning, going back to the case of univariate polynomials, that is the one where the polynomial just depends on one variable. So this will be P1D, so the space of polynomials in two, let's say, okay, this is dehomogenized, but let's say that it's the same if you can directly think about polynomials of degree D. The solution map, what we will do, it will associate the Dirac deltas centered on the points where you have the zeros of your polynomial, time multiplied by the multiplicity of those zeros, renormalized by the total mass, the total number of zeros. Okay, so this is let's say a map going from coefficients to roots. Okay, typically the easy map, let's call it like this, is the other way around. So if you give me the roots, I will give you the polynomial that it's that has that kind of roots just by doing the multiplication of the monomials. And now, okay, so the original plan, I recall you, is to define let's say an optimal transfer distance for polynomials. So we want to do what we want to do. We want then, so to each polynomial we have associated a measure. Now it's time to discuss the distance that you want to put on this family of measures that you have introduced. So let's say that we start analyzing what happens in dimension 1. So for this very simple case. So now what we want to do, we just want to, let's say, compute a distance between this family of measures, okay? And in this case, actually, it's rather simple, but because, I mean, here, what you can think about, so having a family of Dirac deltas just means that you have a collection of d points where you just neglect the order, okay? So you just having Dirac deltas or having, let's say, a family of points where you are not so, you do not care about so much the order of these points, is just the same thing. So let's say that instead of thinking about the space of probability measure, you can take the symmetric product of C, that what it is, you just do C times T times C D times, and then you take the quotient on the space of permutations. So it's just the same thing. And the natural distance will be just to do what? To take the infimum among the representative of this class. That means taking the infimum among all the possible distances, and the minimum is taken on all possible permutations. So, okay, so you have d points, other d points, and then you take the minimum among all possible permutation of the distances between these two dipole of complex points. Okay, so this is just the natural distance coming from here. But it turns out that this is actually the same of doing the Wasserstein distance between this probability measure and the other one. It's just the same, because here you will, let's say, take the infimum among the possible permutation, but it's the same as taking the infimum among all possible way of transporting one family of Dirac mass to the another one. Okay? So let's say that this map will be, again, thinking about what happens in dimension 1. You want also to relate, let's say, this distance to what's going on closer to the discriminant, but let's say, okay, there is let's say that this map, so this distance will be Lipschitz away from the discriminant, but will not be, when you arrive to the discriminant, you might have just Holder continuity. Okay, so now let me maybe just spend, since now we have understood that we can associate to any probability measure, to any homogeneous polynomial probability measures, doing some careful analysis on the multiplicity of zeros, even when you have more than one variable. Then we have analyzed what happens when you have just one variable, that it's the natural distance seeing the space of roots, like the symmetric product of C. So you have two distance coming from this definition to the W2 that just coincide. So now let me just maybe spend a few words saying what it is, this W2 distance, for those of you that are not familiar with optimal transport, and then we will see how we have to implement this object here. So now, so what is this W2? W2, so our setting now is the following. So we have Mg, Riemannian manifold, and we take, let's say we take it compact, so we don't care too much about what's going on for unbounded set. We take mu naught and mu, okay, maybe it's better to use a different notation. Let's do mu1, mu2. That are two probability measures over M. So two measures non-negative with total mass equal to 1. So let's say that mu1 of M is equal to mu2 of M is equal to 1. Then what you want to define is this optimal transfer distance, so this W2 between mu naught and mu1 and mu2. So this will be given by taking the infimum among, so what you want to do, you want to associate to a transportation of one measure to another one a certain cost. So now here I will define what it is, and then I will just spend a few words saying what it is, why is it like this. So what you do, you take the infimum of this function, so you integrate over m times m, the distance squared induced by the Riemannian metric G between x and y, and this function here is integrated with respect to a probability measure on the product space that I denote by pi. You have to integrate with dx dy. And what you're doing, you're taking the infimum over this pi. So not any probability measure, but this pi will be what is called a transport plan. And this will be a probability measure over m times m, that when you project on the first variable, u1, you will get mu1. And when you project on the second variable, you get mu2. So this means that mu1 and mu2 are marginal probabilities of pi. So this graph here means that if you do, so pi1 is the map from the product to the first coordinate, and if you do the push forward of pi, you will get just mu1, and if you do the push forward of pi with respect to the projection on the second coordinate, you will get the second measure. So this means basically that pi is a generalized way of sending mu1 to mu2. Okay? And what you want to do, you want to take among all possible transport plan, you take the infimum of this cost here. So this is the Wasserstein distance, the optimal transport distance between mu naught and mu1. Okay? So this will be, this one defines a W2 distance that makes the space of probability measure with this W2 metric a complete separable metric space, okay? That is also geodesic. Okay, so and now what the plan is to do, to take this distance and to apply to any other, between any two polynomials. But there is some caveat, let's say, so because now what we are doing, so let's do once again our picture. So here we have our linear space that is P and D. Here we have our P of CPN, that it's just a metric space. We have devised, let's say, that is map mu, an embedding of mu of P and D here inside. Let's say that will be like this. So this will be mu of P and D. Now our point is that we want to define a reasonable distance of deformation of our polynomial from here to here. So let's say that this one is mu of P1. Here you have, let's say, of P0, and here you have mu of P1. And what you want to do, you just do not want to, let's say, define the distance from here to here by taking the W2 distance, but let's say I want to take a deformation of this polynomial, of this measure, into these other measures, just by remaining inside the image of my let's say, homeomorphism mu. So saying in other words, I just want to allow path for going from my first polynomial to another polynomial, just moving inside the space of probability measures obtained via mu. Okay, I just want to move from one measures to another one, remaining inside the image of mu, because I just want to define a W2 distance inside my space of admissible measures, because I do not want to, let's say, take a path that it's not taking care of the fact that I'm transporting polynomials. So in the case n equal 1, so when with a univariate polynomial, you know that we have already discussed the fact that the map mu associates to a polynomial just a family of Dirac masses, and this is a convex set. The image will be a W2 convex set, meaning that if I'm taking two family of Dirac mass, I'm taking the Wasserstein geodesic, they will be again family of Dirac mass. So this means that the image of mu will be geodesically convex. Okay. So these issues does not appear. But in general, this is not the case. So in general, mu of P and D will not be geodesically convex inside the space of probability measure. And then what you have to do, you have to induce, as you would do on a, so now we have to think about P of CPN like a geodesic metric space. You have a subset that would say that it's not geodesically convex, and you have to induce the length structure of this on this object here. So you have to minimize a certain distance to induce the right distance. Okay, so now let's do a step back and see, so what is the situation? So the situation now will be that we have a metric space that is a geodesic, and we want to induce the length structure on a subset that is potentially not geodesically convex. So what is the way in which you do it is the following one. So this will be just one slide on metric geometry, will be very simple. So what we have a metric space that you have to think about like to be P of CPN's space of probability measure with a W2 distance. So it will be possibly of infinite dimension, whatever this means. And if you take a curve that it's what is called absolutely continuous AC2, we say that this is AC2 if and only if there exists an L2 function over the interval such that the distance between gamma t and gamma s is bounded from above by this interval from s to t of this function n. This function gamma, so curve will be absolutely continuous of power 2. Then you can define the metric speed, that will be just the limit of the distance between subsequent points. So you're taking just the incremental ratio, but with the distance without, because this is the only thing that you can do. And if the curve is AC2, you see that this function here will be in L2 and will be the energy of the curve. And this metric space will be called a length space if you can recover the distance by taking the infimum among all possible energies with AC2 curve. Okay? If this infimum becomes a minimum, then the space is called geodesic. In our situation, our metric space, it's a geodesic metric space. So the space of probability measure with the W2 distance is a geodesic metric space. So we do the same thing with our situation. So now we take the space of the path, the space of admissible path. So this will be, so here we will have P0 and here we have P1. So the space of admissible path here over P and D will be the space of paths such that when I see them via mu, so this will be mu of PT, this will have to be an AC2 function with values in the space of probability measures, okay? In the Wasserstein space. And we define let's say its energy, the energy of this curve will be what? The integral of what is called the metric speed of this curve. So now this will be exactly what? So now we just apply the definition that I brought here, but where here the distance you have to think about is the Wasserstein distance, okay? So we have a curve here. This will be admissible if the image will be an AC2 curve in W2, and what we define, its energy will be the integral of the metric speed raised to the power 2. This mu dot, the modulus is the metric speed. And to recover the inner distance, you have to minimize among just the possible admissible curves. So let's say that if I want to connect from here to here, I'm confined to just moving and to remain inside. And I have to take this infimum. This is still, let's say, a rather abstract construction. You basically can do anytime you like. So as soon as you are in a metric space, that it's a length space, you have a subset, you induce the length structure just by doing this construction. This is nothing new. It's actually a rather standard thing to do. So the important thing to do now is to say properties about this W2 inner distance, okay? And this is our contribution says in the fact that we managed to write down explicitly what is this W2 inner Wasserstein distance. That you recall, now by pulling back this structure from CPN to PND will be a distance defined on PND, okay? So what is now the hard part of the story? The hard part of the story is exactly here, because what you need to do, you need to calculate the metric speed the metric speed of a family of, let's say, of a curve of polynomials moving here. And this metric speed will have to deal with the fact that you have to compute the infinitesimal variation of the W2 distance between the polynomial time t and a time t plus epsilon. This is the tricky part, I mean, let's say the hard part of the work that will not be discussing too much. I just want to tell you that usually it's very, I mean, it's out of reach to compute. If you take any strange subset, I do not know many examples in which you are able to compute precisely this metric speed. It's very hard, typically. Here, the fact that we are transporting probability measures induced by polynomials gives a lot of rigidity that permits you to, let's say, make a lot of restrictions on the family, on the deformation that you are doing, okay? And this is exactly what I'm mentioning here. This is what is called the Hamiltonian Thom isotopy lemma that says the following one, that if I have a family, a curve of polynomial pt that do not go through the discriminant, not going through the discriminant is kind of transversal condition. This says to you that there exists an Hamiltonian isotopy, that just means a map from CPN to CPN, depending on time t, that at 0 is the identity, that maps the 0 set at time 0 to the 0 set at time t. So this fact that this Hamiltonian isotopy, what it means? It means that it's a family of smooth diffeomorphism that at time 0 is the identity, and the vector field giving you this transformation is actually induced by its Hamiltonian, because here you are moving inside CPN, that it's a symplectic manifold, and you use this structure very much. So the way to compute this metric speed is the fact that if I'm taking a family of a curve of polynomials not going through these bad points of the discriminant, this deformation is given by an Hamiltonian isotopy. So I have a smooth family of diffeomorphism mapping my 0 set at time 0 to the 0 set at time t via an Hamiltonian vector field. And moreover, this map preserves, since it's Hamiltonian, preserve the volume, so let's say the symplectic form, and therefore also the volume measure. So this is exactly the way in which you can track the evolution of this measure here. This is the first point. The second point is that you have, okay, so now this is, let's say you have understood how the 0 set moves, then you have to compute the metric speed in terms of optimal transport. And this is a bit tricky. You have to look at how you can, let's say you have to study what is called the tangent space of W2, that will be the so-called space of gradients. That, I mean, to some extent, so there is a certain amount of work, of non-trivial work, to understand the exact form of this object here. So, but the point is that you have an Hamiltonian structure that kicks in, that is given by the fact that you are deforming a special family of measures, and then this Hamiltonian structure permits you to compute really precisely the metric speed. And in the end, this is what we have finally achieved. So for a given curve Pt, so a family of polynomials not going through the discriminant, so their energy is computed like in this form. So maybe this integral from 0 to 1, it's not relevant, because now the important part is this one, that it's this one, it's the metric speed. So let's have a look at the metric speed, what it is. So you are integrating over the 0 set of the polynomial at time t, and you are integrating 1 over the gradient of pt squared, and at the numerator you have the time derivative of the coefficients of the polynomial. So this pt you have always to think about as a function defined here, okay? And so again, the important part, conceptual part, is that, okay, here the set z of pt is not really explicit, but this is just defined in terms of the coefficient defined the polynomial, okay? The other nice thing that we liked a lot is the fact that you are, let's say, integrating, giving this formula for polynomial not going through the discriminant, and indeed here you have a penalization to the fact that you arrive close to the discriminant, because you are integrating over the 0 set, 1 over the discriminant, sorry, 1 over the modulus of the gradient squared. So this means that, I recall that the discriminant set is exactly where you have a point that annihilate both the polynomial and the gradient. So somehow your energy try to avoid being on the discriminant, even though it's just been defined outside of the discriminant. Okay, so this is the energy induced by the W2 structure over CPN. So let's summarize what we at the end have obtained. So for any two polynomials, the first thing that we have proved is that this distance is actually finite. This is non-trivial because we have to show that it is admissible. I mean, no, because this is, you see, now let's go back. The first thing that you have to be sure is that, I mean, for instance, if you take a linear curve going, let's say a linear interpolation from one polynomial to the other one, you're not sure that you're not going through the discriminant. So you have to be careful in proving that this energy is actually finite for any given two. So you have to be careful by proving that if you give me two polynomials, I'm able to find a curve with finite energy. This took us a certain amount of time because, again, you have no control once that you define a curve on the space of polynomial just in terms of the coefficients, that you stay away from the discriminant. So you have to be careful and, let's say, devise a way in which you maybe eventually touch the discriminant but still remaining with a finite energy. Complex norms. No, yes, I mean, this is DZ means that I'm integrating with respect to the volume form. Yes, yes, here I was a bit sloppy. Yes, yes. Or if you want, you can, instead of being CP1, you can put yourself on the sphere. So you take the representative on the sphere of the zero and you have to. So this is what we call the inner W2 distance. So what we have proved is that with this distance, this will be a complete and separable and geodesic metric space for any two. So even more, this energy here defined like this is actually is an Hermitian metric, away of the discriminant, and again, away from the discriminant, this form is actually Keller. So we have actually, the interesting thing is that the W2 induces a Keller structure on the space of polynomials. Okay, and yes, so this is the Hermitian metric is written in this form, exactly I was mentioning before, and okay, so this is the fact that it's Keller is not emitted from here. There is another representation of this metric coming from the fact that it has to do with a couple of projections. It's not really there, but you can prove that there is also a Keller structure behind. So here, let's say the good news. The bad news so far is that, for instance, it's not clear the convex. So let's say the compactness property of this metric space is not clear so far. What we managed to prove is that if you are, let's say, far away from the discriminant, let's say if you take an epsilon neighborhood of the discriminant in the Fubini study distance, so here, okay, so you just remove an epsilon neighborhood in the Fubini study distance of the discriminant. On the complement, you are compact with respect to the W2 inner metric, but otherwise it's not. Let's say we can regard it as an open problem, as an open question that we still are not able to answer in its full generality. Okay, so a couple of applications. Maybe I have time just for the second one. So briefly, I will not go through the details. So the first one is that, okay, there was a certain amount of effort to understand what is the relation between the regularity. Let's say that you pick a family of polynomials, so that the coefficients will depend on a certain function that depends on time. Let's say that you ask for a certain regularity of the coefficients define your polynomial. So you have, let's say, a curve of polynomials, C infinity. Then you ask yourself, what is the best regularity that you can get for a continuous selection of a zero set of a zero. Okay, and what Paruziski and Reiner proved is that what you can do is that you cannot get any better than W1P with P strictly less than D over D minus 1, just for univariate polynomials. So this means that if I'm taking a smooth family of polynomials, I'm tracking the path of a zero. So I'm saying this zero as a curve over C, and I'm asking myself, what is the regularity of this curve? The best you can do is W1P, not better than that. Let's say that what we did, I just want to be very quick, because I want to then skip to the second application, that we generalized this result to the case of multivariate polynomials. And instead of looking at tracking just one single root, we reformulate this result by tracking the probability measure, okay? So the measure moving here. So if I have a smooth family of polynomials, so a smooth curve of CK1 from the interval 0, 1 to the space of polynomials, so this means that the coefficient will be a function of order with k derivative, and the k derivative to be so Lipschitz. Then the corresponding curve mu will be ACQ with values in the space of Wasserstein space. Okay, so this is just very quickly. There is some details, but they are not important. So I just want to spend more time speaking about the second application, because it has to do with the special form of the energy that we have found. So a little step back. So I want to say 2 words about this Smale 17 problem. It's one of the list of Smale problems, and you can find also on on Wikipedia, wherever. So it asks for the following question: so to find an algorithm that finds zeros of P in a polynomial time, where here there are some caveat. I mean, this sentence should be made precise by saying that there are some genericity around, but let's say that for the moment, with some error, we say that this is the Smale problem. So to find an algorithm that gives you in polynomial time an approximate zeros of our polynomial, okay? This has been solved, okay? So we are not proposing any new solution to whatever. So this problem has been already settled by a list of great contribution by people working on algorithm and other stuff. So by a series of work by Beltran, Pardo, Hooker, Burgiser, and Lere. So they followed this kind of approach, what is called the homotopy method. So let's say that we want to solve this Smale problem for a polynomial P1, okay? So P1 is a polynomial for which we want to find the zeros that we want to find, okay? So P1, you're giving me P1, I need to find the zeros of P1 via this algorithm. So this homotopy method goes like this, okay? Let's say start from P0, another polynomial, from which we know its zeros. And then what you do, you just do the linear homotopy from P0 to P1. So you define Pt to be 1 minus T P0 plus T P1. You consider the linear homotopy, and you try to do a continuation of your zeros that you know on P0 using a Newton method. So on P0, you know the zero, and then you try to continue this zero via the Newton method, okay? Until you, obviously, Newton method will give you an approximate zero, and you want this method, so this iteration, to arrive until time 1, in which you will find an approximate zero of P1. Let's say via some dimensional consideration, since the discriminant has codimension 2, we are always able to find, let's say, Pt that does not go through to the discriminant, but let's say the way in which, so let's say the complexity in the sense of Schubert-Smale of this algorithm, so the amount of time that you need to run this algorithm, it's bounded in terms of the distance of Pt from the discriminant. So if Pt goes too close to the discriminant, the running time of this algorithm explodes. So a way from which you can approach this problem is to construct, let's say, bound, let me say it better, to find, given P1, find P0 in a smart way so that Pt stays away by a certain safe amount from the discriminant, okay? And so this was the approach run by Lere, Burgiser, and Curie. So Cook, in a very smart way, P0 so that Pt is sufficiently far away from the discriminant, that there was, let's say, a probabilistic approach, then it was so there was, let's say, a random algorithm, then it was the randomized. So anyway, so this was in a very few words, so the underground idea behind this approach. However, there was this original idea of Schub, not using linear homotopy, but instead, why don't we change the metric on the space of polynomial and induce and consider what is called the condition distance. So what you do, you multiply the classical Fubini study metric of P and G by 1 over the distance squared from the discriminant. Okay, so you penalize the fact that you arrive to the discriminant. In this way, the geodesics of this metric will necessarily avoid by a safe amount the discriminant, okay, of your manifold. And one of the, I mean, there is a series of incredible papers on this Schub, on this Mel 17 problem. That is Schub's Mel saga. So there are 6 papers, and in one of those 6 papers, they prove that if you give me a curve PT of polynomials, the Newton steps to continue these zeros along PT will be require this quantity as a time. Okay, so this will be the length in the condition distance, in the condition metric, sorry, of your curve PT, where the condition metric is the one obtained by taking the Fubini study divided by the distance squared. Okay, so this distance is actually rather important for the Newton step. And so the original idea of Schub was to provide some uniform separation from the discriminant along this condition geodesic. But let's say the Schub conjecture was indeed that this distance here squared should be what is called self-convex. That means that if you compose it with the log, so the log of the distance from the discriminant 1 over 2 should be convex along condition geodesic. This was actually not really solved, so because at the end the approach to Smale problem follow another path, but let's say that our approach, let's say our energy is actually going exactly in this direction, and we managed to prove this log convexity at least in dimension 1, okay? And why it goes in this direction? Because our distance is actually, so our energy contains this term here, so the distance from the discriminant, that one that we have commented before, in an integral, in an L2 form. So we have the integral over the 0 set of 1 over the gradient of the polynomial that has to be understood like the distance from there. So let's say we have solved this, let's say, Schub conjecture by, in dimension n equal 1, coming from this W2 distance. In more general situation, I think it's a very interesting problem that we are still not able to do it. Okay, so I think my time is almost finished, so let me just conclude with 2 open problems. So the first one is the compactness. Still, it's not clear. So this metric space, the space of polynomial with the W2 inner distance, still is not clear if it is compact or not. This seems to be a very trivial question, but actually it is not. Okay, because it's true that, just to make a comment on, a general comment on this problem, so you have P and D, you have put it inside, that is map mu over the space of probability measure with the 2W2 distance over CPN. This is compact. And then you would like the, let's say, the pullback of the distance here should be compact as well. This is not really the case. It's not, I mean, it is not that it's not really the case, we don't know. But it's, there are examples of metric spaces compact on which you consider a closed subset so that the inner metric results in a non-compact set, non-compact metric space. For instance, let's say that we put ourselves into the square, so this is just 0, 1 square. This is just a perfectly compact metric space, and then you take just a line bending like this and arriving to the x-axis. So let's say that this will be our closed subset. So this will be just all of this, the union of all of these lines that I've drawn here will be our set C, our closed subset, because I'm taking just, let's say, rational, I don't know, just a sequence of slopes going to 0. I'm just taking the union. This will be a closed subset. But with the induced length structure, this will be not compact, okay? So once that you take, even if you are in a compact space, once that you do you put a closed set here inside, this will be again closed. With the induced length structure, it's not clear if it is compact or not, because you may have done a lot of bendings, a lot of strange things, so that at the end you lose the original compactness, because maybe you can keep turning around. So compactness, still not very clear. Let me just give you one additional comment that this kind of thing that we have done has some similarities with the moduli spaces of certain general construction. Let me just mention that this distance has the same flavor of a Weil-Petersson type metric, and if you go and if you look for some similarity, for instance, the Teichmüller spaces sometimes fails to be compact. So it might be that it's compact, it might be that it's not. We are not still have a clear idea on why it's not or not. And the other open problem that we would like to address, but still also on this one we haven't succeeded so far, is to prove that what we really would like to have is that outside of the complement of the discriminant should be geodesically convex with respect to the W2 on the inner W2 distance. So this is our, let's say, hope. Again, why is it so? Because, again, in the energy, we have this very bad penalization. We have 1 over the gradient square. So a geodesic should try to remain bound and then avoid the explosion of the disk of 1 over the gradient. So it means that the gradient should never annihilate on the 0 set. So you should remain away from the discriminant. So far, we know just for n equal 1, this was already clear by some basic techniques of optimal transport. And also we know it for quadrics. So when the degree is equal to 2, we have 2 PhD students working on it, and they think that they have managed to prove it after a lot of effort, but seems that it might be the case. But anyway, all the other cases are rather unclear. So if you have any insight or idea, we will be very happy to listen any suggestion. And I think, yeah, it's not going because it's finished my talk, and thank you for the attention. Yes.
Thank you for the nice talk. So questions?
Can you, do you have any idea what these geodesics look like in some examples? Can you simulate them or something?
No, this is would be very nice to have, but this is also, yes, another thing that we would like really to. I mean, in dimension 1, so for univariate polynomial, we know it because it's just a matter of the fact that you have n points here and points there. You just do this minimization on the space of permutation, and then you just take the linear interpolation between, sorry, not the linear interpolation, just the geodesic interpolation between the points. So maybe I can just. But yes, so the bad part of the story so far is that you would like to, let's say, write down the equation of geodesics in terms of the coefficient of the polynomial, but this is not, it's not easy to write down the equation of geodesics. So if you, nabla gamma dot equal to 0 in terms of the coefficients, this is not clear because we have an integral energy on the 0 set, and still, I think there is still some insight that we have to understand a little bit better. But otherwise, let's say if we are just in the case n equal to 1, we have to think about it here. Maybe we'll have d points. And here we have, with their multiplicity, here we have other d points. You do the optimal matching problem. That means you minimize. So let's call this one xi, and here you call it yj, you minimize xi minus y sigma I over all the permutations. And once that you have found the optimal permutation, means that you have just a matching between each of these single points to just a single point here. This is a structure theorem on the optimal transport. So this will be kind of a map. If you're outside of the discriminant, if you have d points uniformly distributed, so each of these points has mass 1 over d, other d points with mass 1 over d, then the optimal transport, it's just a bijective map. You have no 2 points going to 1. And so once that you have the, let's say, the optimal matching, what you do, you just take the Fubini study geodesics in CP1, and here you have at time t, you just take the, let's say, so this would be just, yeah, the Dirac deltas over gamma t. Some, this would be, let's say, okay. It is like this, but this is, let's say, already well known before. But yeah, we would be very happy to know some simulations, but we are not very good with simulations, let's say.
Other questions? So I have a naive question. So in this slide and the second application of your methods, so it seems that the case when n equals 1 is much simpler than the case when n
Yes.
is at least bigger than 1.
Yes.
So what kind of nice properties when you use in all these quiz problems? Why
n equal 1 is simpler?
Yes.
Yeah, because the image of the homeomorphisms is convex. So they have an explicit description of geodesics.
Okay.
So everything boils down to the fact that you have an explicit expression of for geodesics. This is the bulk of the. So geodesics are easy to describe. They're just lift of this geodesic once that you have the matching. But yeah, I mean, it's yeah. Let me say that it was just. I would like to say that it's just the beginning because it's the first, our first tentative in this direction. So this is just our first paper on this. So now we are keep going with our investigation. We hope to be able to say a little bit more of the compactness and geodesics on the geodesic convexity of especially this second property would be, I think, very nice because it would mean that you will have a natural way of deforming a polynomial into another one by avoiding strange things. So usually this is not an easy task to do, no? Because you have no way of controlling the geometry of your deformation. So this would be, let's say that the positive part is that we have let's say, there is a natural distance, W2 distance, that seems to have an important role in these things. That's that.
Any other question? Okay, if not, let's thank Professor Cavalletti again.
Thanks.
And let's have a 10 minutes break.